Okay, well, I'm going to go ahead and get started. So welcome to the 12th FEM at LLNL seminar. We've been doing this for a year at this point, and I think we're going pretty strong. We plan to continue this into next year. We're going to put a whole bunch of talks together next year. But yeah, this has been an excellent year. I've learned a lot along the road, and I'm looking forward to us continuing to do this. But right now, I'd like to introduce Lin Mu. She's an assistant professor at the Department of Mathematics in the University of Georgia, where she's doing research on higher order numerical methods for solving PDEs, uncertainty quantification, stochastic PDEs. And she applies some of these methods to computational biology as well. So Lin, why don't you go ahead and take it away?
Okay, thank you. Thank you very much for the introduction, and also thank you very much for the invitation. It's my pleasure to give a talk about our recent research funding for the efficient and effective finite element solver for the diffusion equation with strong anisotropy. So this is a joint work. Oops. Okay, this is a joint work with Dr. David Green. He was working at Oak Ridge National Lab, but now he moved to Australia. And Professor Xiaozhe Hu, he is in the math department at Tufts University. And Jeremy Lau, he is a fusion scientist working at Oak Ridge National Lab. And also my collaborator, Dr. Mark Stewell, he's from Lawrence Livermore National Laboratory. So we began with this project around last summer during our MAPS meeting. So Mark actually bring about this topic. We are talking about the transport equation with strong anisotropy, and I'm from the math part, so I try to develop a good solver for solving the related problem. So we began with this project, and we made some progress in this field, and I will share some progress in this research topic. Okay, so here is the outline for my talk. I'm going to talk about the 5 sections. First, I will start with the introduction for motivation and the background. Then we'll talk some previous work and deal with the 2 issues in the related problem. They are the accuracy problem and the efficiency problem. Then this talk will be ended with concluding remarks and the future work plan. Okay, so first, I would like to congratulations for the achievement for the fusion breakthrough at the Livermore National Lab. And I tried to find some time to watch about the live streaming, but I was attending students' oral presentation, so I missed that. I will catch up about this breakthrough later. Okay, so this one was achieved for the first time for the net energy gain from the fusion energy by the NIF facility at Livermore Oak Ridge, at the Lawrence Livermore National Lab. For our project, we also talk about the fusion energy. So we talk about the tokamak device. This one is a device to use the fusion energy to generate unlimited energy. And I take the video from the ITER website. Let me show this big picture again. So we actually use this device to hold plasma in the vessel, use a very strong magnetic field and high temperature to use the fusion to generate energy. Let's go back to our math problem. We focus on the magnetic confined plasma application. In our focus on the anisotropic is generated by the strong magnetic field. Here is the cross-section for the tokamak device. Let's use d parallel for the parallel direction constant for this value, and the d perpendicular will be another constant denote the perpendicular direction. Both of them are constants. This ratio will denote the anisotropic ratio. This ratio can be very huge. For example, inside of the core region, it can be up to 10 with 12 as the power in the core region. Then as the boundary part, this value may be relatively smaller, but still large. It can be 10 up to 6 in the boundary region. Okay, because of the huge ratio, like this large, so the traditional method may give us very bad numerical solution. We will call this one numerical pollution. Okay, so this is due to the fast parallel dynamics comparing to the perpendicular dynamics. The traditional method to resolve the numerical pollution is to use the field aligned mesh. For example, one can use this software or use Edge to generate pretty good numerical approximation to avoid the pollution issue. But for our application, we care about the fast creep region, which is here. They are the regions for the antenna and the device wall. So usually, it's very hard to generate aligned mesh. So this one will motivate our research on the numerical solver on the non-aligned mesh. Okay, so let's take a look about the difference in isotropic diffusion equation and anisotropic diffusion equation. For isotropic diffusion, the diffusion will be uniform around all directions. But for anisotropic diffusion, the problem may have some preferred direction for the direction. So I list some incomplete reference for these two methods. So roughly, I divide the research to the aligned mesh and the non-aligned mesh. In the aligned mesh method, you can use the flex aligned coordinate in the finite difference method. I'll use aligned mesh in finite volume or the adaptive mesh in finite element method to resolve the numerical pollution. By using the non-aligned mesh, so you can use the modified interpolation scheme in finite difference method. I'll use high order method in the finite volume method, finite element method, or spectrum method to get a very good numerical solution. In our method, our approach also in this category, we will use finite element method with high order scheme. Then for the corresponding linear system, due to the high anisotropy ratio and very fine mesh or very high order in the scheme, the problem will give us very challenging linear system to solve. So we also may need fast solver in order to solve the problem efficiently. For the fast solver, one may consider about Schwartz multi-level or multi-gram method to solve that. I'll use subspace correction or auxiliary space preconditioner. For our problem, we'll use auxiliary space preconditioner. We will talk about these two approaches in the later slide. Okay, then a little bit of preview about this project. We will address the issue in the diffusion equation with strong anisotropy. For our problem, this ratio D parallel over D perpendicular is bigger than YE positive 6. We will address these two issues related with accuracy and efficiency. Our method is based on non-aligned mesh, and we will construct the efficient solver to solve the corresponding linear system. For the accuracy, we will use high-order finite element scheme. For the efficiency, we will construct the effective preconditioner to solve this one efficiently. Okay, so let's go back to the math. So we will consider about the steady state anisotropic diffusion equation, which is described as equation number 1 coupled with, for example, the homogeneous Dirichlet boundary condition. Okay, here this D is a tensor for the two-dimensional problem. We can represent that this one as the product of 3 submatrices. So the first one is given by the unit vector B. For example, it can represent the magnetic field. We have 2 components, B1 and B2. They can be functions about the spatial variables. Then for the middle matrix, we have D parallel and D perpendicular. These two, they are 2 constants, represent the parallel and the perpendicular diffusion coefficient. For simplicity, let's assume we only care about D perpendicular equals to 1 and the D parallel with varying values. Okay, now let's introduce about several schemes. We will use the continuous Galerkin scheme and the discontinuous Galerkin scheme. So when we have a domain, we will do the triangulation. And based on each element in the triangulation, we will assume our bases, they are piecewise polynomial with a certain degree. For example, let's use K as a degree for the polynomial. If we require the continuity across the edge, we are in this H1 FEM or CG FEM. Okay, if we relax about the continuity condition, we can consider about the DG scheme by using this L2 basis function. Following comparing about the DOF in CG and DG. For example, let's use P4 as the basis function. So for CG method, we can see the degree of freedom are on the interior, the boundary, and the vertex. So for the DG element, we can see we have some duplication of the edge degrees of freedom. So basically, we can check the difference between CG and DG. For DG method, we need more degree of freedom. So if we want to use DG, there must be a good reason to use DG method. Okay, for the CG method, we are going to solve the numerical solution belongs to the CG finite element space such that equation number 5 is satisfied. And ACG will be a bilinear form defined by equation number 6. So as we can see here, the bilinear form is very simple. It's almost similar as the weak formulation about the original problem. Okay, so there are some remarks about the CG method. So usually CG method have the fewest degree of freedom and the simplest bilinear form. However, the drawback for CG is the conservation law. Usually, it's very hard to require the CG method satisfy certain conservation law. So if our problem, for example, is time-dependent problem or the transport problem, which is sensitive about this fundamental conservation property, CG method may be not good to solve the related problem. So in our setting, we will only use CG method to construct preconditioner, but the solver for our problem is DG method. Okay, for DG method, we are use the discontinuous functions to do the approximation. We will find the numerical solution belongs to this VDG finite element space, such that equation number 7 is satisfied. So the bilinear form ADG is defined as this one. We have several parameters in the scheme. We have beta and alpha. Okay, in order to weakly enforce the continuity across the boundary, we need this alpha and beta. For beta equals to 1, we can have the symmetric IPDG scheme. If beta equals to -1, we'll have the non-symmetric IPDG scheme. If we prefer symmetric IPDG scheme, that means beta equals to 1, then the penalty parameter alpha have to be chosen big enough to ensure the stability. Okay, so there are some good reasons to use DG method because we have the mesh flexibility or the conservation guaranteed property. So for the transport equation, we prefer DG method, and we'll use DG method to solve our problem. Okay, then let's talk a little bit about the penalty parameter. So for the penalty parameter, we need this one big enough for the symmetric IPDG scheme. So we can choose alpha 1 or alpha 2. Okay, so for alpha 1 and alpha 2, we did the numerical test. So alpha 2 actually behaves better in comparing to alpha 1. So for our numerical test, we'll choose alpha 2 and check about the other performance. Then if we do the error estimate rigorously, one may find the error measured by the L2 norm is bounded by some constant times C power times H power K plus 1 and some norm in terms of the exact solution U. Okay, then this factor is lambda maximum over lambda minimum. Usually lambda minimum equals to 1 for our problem. Then we have lambda maximum equals to D parallel. Okay. Then if we check about the strong anisotropic problem, this ratio is up to 10 with power 6, which means it's very big for this one. Okay. Now, because of the error is big, that means the numerical solution actually is far away from the exact solution. In order to get a very accurate numerical approximation, so we can think if we reduce the value in H, this one will be smaller, and the product about a big constant times a smaller value may help a little bit. Another way is to increase this K. K is a polynomial's degree. So if we have high order scheme, this decaying factor may help about our numerical solution and help us get a more accurate numerical approximation. Okay, so that's our idea. We will use big value in K and get a more accurate numerical solution. The other related problem for the linear system is if K is big or H is small or this factor is very big, we may have very bad linear system to solve. So we also need to care about the linear solver. Okay, so that's two related issue about this problem. Okay, now let's do some numerical tests as the motivation. So we care about a unit square. Okay, so on the edge x equals to 0, let's consider about the Dirichlet boundary condition. On the other three edges, let's enforce the Neumann boundary condition. So for the manufactured solution, we will choose u equals to this one, 1 over pi squared times sine pi x. And the right-hand side of false function is computed by our scheme. It's just a simple sine function. Okay, now for this test, we will choose B as a unit vector pointing up. Okay, so we will test the problem on the aligned mesh, which is shown as the left figure, and the non-aligned mesh, which is shown as the right figure. Okay, now let's vary the value in the anisotropic ratio. For D perpendicular, we'll choose it as 1. For D parallel, we'll choose different value. If D parallel equals to 1, we are dealing with isotropic case. So left figure plot the numerical performance for the isotropic case. We will do the numerical simulation on the aligned mesh and the non-aligned mesh, and plot the trace plot, which is y equals to, for example, 0.9. So we plot the trace plot and comparing about the numerical performance. So both of them for the linear finite element method based on the mesh with size 1 over 16, they are aligning with exact solution. So that means our numerical solution are good, aligning with the exact solution. Now let's take D parallel to be a big value, which is 10 with power 9. Okay, by using aligned mesh linear case, h equals to 1 over 16, which is this green dotted curve. It's just behind the exact solution. So still the aligned mesh gave us very good numerical solution on the very low order of the scheme. Now let's try non-aligned mesh with k equals to 1 and h equals to 1 over 16. It's this one. It's this purple curve. So it's very far away from the exact solution. That means the numerical approximation is very bad. Now let's increase the order. For k equals to 2, we will have this blue curve, which is approaching to the exact solution. Okay. Now if we increase the order even more, k equals to 4, it's this darker purple curve, which is almost aligned with the exact solution. So this tells us the high order method works and can help us get very accurate numerical solution for this simple test. Okay, now let's check about this one for the annulus domain. For this domain, we'll consider about the ring shape. The outer radius is 1, the inner radius is 0.5. Okay, the exact solution is chosen as this sine function. Okay, then the magnetic field is this circular vector. Then the right-hand side function is computed by the problem. Okay, now let's choose the numerical test on different mesh with different polynomial. For example, we will choose the division number for the radius direction as 1, 0, 24 with linear DG method. Okay, then we consider about the scheme and plot the numeric and plot the arrow. The L2 arrow is 5.8 E negative 2, and the related DOF is 2.5 million, and the condition number is very large. Now let's try about the quadratic finite element scheme to achieve the similar arrow. For the similar arrow, we only need DOF as 0.1 million, and the condition number is actually decreased, and the problem is better to solve. Then let's increase the polynomial degree even more. Consider about k equals to 3. Then for this case, we only need nr equals to 8, which gives us DOF 5k to achieve the similar arrow. Okay, so this one just show us very efficiently by using high order method, and our scheme can give us very good numerical solution. Let's try about an even more challenging test. For this test, B is changing direction, and B is some function related with special variable. Okay, now we plot the B as this arrow plot, and the contour plot for U, and the color plot for the exact solution U is shown as the right figure. Okay, let's test about some arrow profile and convergence order for different values in H and different values in the ratio, anisotropic ratio, and the different polynomials degree. Here are the results for the related parameter setting. As we can see here, by using high order method, our solution is better. And if H is fine enough, our K is high enough, when we resolve the anisotropy, we can observe the optimal rate in convergence. Also, another issue is here, by using high order method, actually here this accuracy may be not good. This is because we are using direct solver, and the accuracy is limited about our solver because our problem is very hard to solve with very bad condition number. So that will limit about our accuracy. Okay, so we also want to resolve that problem in the later slide. Okay, now a little bit summary about what we have observed. We have observed high order scheme works well for resolving the non-alignment mesh and the high anisotropy in the problem. But with the increasing anisotropic ratio, the condition number for the linear system is also increasing. And here is a figure to demonstrate that. By increasing the level for D parallel, okay, we can observe for K equals to 2, 4, and 6, the condition number is increasing significantly. Okay, so this one means we will have worse and worse linear system to solve, and we definitely need some good faster linear solver to deal with this issue. We may also observe for the linear case, the condition number is limited by some constant. Okay, so this is because the linear element is very hard to resolve anisotropy, and the condition number for that is also limited by h, but not the anisotropy, and we can observe this constant coefficient. Constant behavior for the condition number. This one also tells us by linear method, if the mesh is not fine enough, we cannot get the very good numerical solution. Okay, so this motivates the second part about our research. We need effective and efficient fast solver. Probably I will pause a little bit and take your questions, and let me know if you have any questions about our high order numerical solver. Okay, so I will continue with the second part. Okay, now we will need the fast solver to efficiently solve our corresponding linear system. The method we are going to use is auxiliary space preconditioner. Let's go back to the multi-grade V-cycle method. So if our problem is on the finest grade, let's see the size is small h, but it's too expensive to solve because the linear system maybe is too big. Our condition number is too large. Okay, we will go down by counting the grade. For example, we count this grade several level. At some level, our computer can handle the direct solver. So we will perform direct solver at the coarse level, then go up and down to solve our original problem. So the step for going up and down is smoother. Smoother is to smooth out the high frequency in the residual error. Okay, so this is the classical multi-grade V-cycle method. Auxiliary space preconditioner is very similar to this one, but the difference is we replace the coarse level solver by another scheme. So for example, let's think about we are using the continuous Galerkin scheme with the same order on the same mesh. So we will solve the problem at the CG with the order K, then go up and down to get the numerical solver for our DG scheme. Okay, so because we only go down once, this one gives us the one level auxiliary space preconditioner. We can do even more. Okay, so for example, we can do the multi-grade phenomenon. We will use multi-grade to replace the exact solver about this step. Okay, and then we will go down and go up to achieve the multi-grade auxiliary space preconditioner. So we will use one level and multi-level to solve the problem and compare the performance. Okay, so why we need the CG method as the ASP? Because the CG method has less degrees of freedom and it's easy to compute and formulate. And the CG method actually has a lot of well-developed CG fast solver, and we can take advantage about that and help with our actually the practical DG solver. And that's the reason why we use the CG as the auxiliary space preconditioner. Okay, so let's check about the ASP for our DG method. Let's form the problem as a linear matrix ADG and right-hand side. So we are going to solve U from this system. Okay, so this space for DG space can be represented by a product of two spaces, we can use VDG and VCG. Okay, now because CG is a subset of DG method, actually we can use a subset decomposition for the VDG method. Now we can construct our auxiliary space preconditioner as following. So BDG is used to approximate ADG inverse. Okay, so BDG can be formed as two parts. One is a smoother. We can use Gauss-Seidel as a smoother. And the second part is our exact solver from CG method, A inverse. And this pi is a mapping connect DG space and CG space. Okay, so we can use some inclusion operator or L2 projection to connect the VCG and the VDG. Okay, and you can see we need A inverse exactly, and we'll call this one level ASP. Okay, so let's test this. We will choose our preconditioner as this one, and choose GMRS method with tolerance 1e-6 in the test. So for this test, we'll choose the triangular mesh on the unit square with B equals to a unit vector 0 and 1. Okay, so for this test, we can see for different values in D parallel and different values for the polynomial degree. Okay, we can observe constant behavior for increasing K or increasing D parallel. So this one means our method is robust with respect to K and D parallel. Okay, now we observe the effectiveness and the robustness for the scheme. However, for exact inversion about the ACG, it may be still challenged because the system may be with very large size and a high polynomial degree and strong anisotropy. So this one still have very bad condition number, and it's very challenging to invert that. We will make use of the multi-grade phenomenon and replace this ACG by another preconditioner. Okay, so for here, we will replace the exact inversion by the preconditioner. For example, we will use BCG to approximate ACG inverse. And here, BCG will be some smoother and the multi-grade preconditioner B. Okay, so for the SCG smoother, we can use the Schwarz type of the block line smoother as suggested by the reference. So this one will be also the major contribution about our work, how to construct the effective line smoother. Okay, so let's talk about the smoother. So smoother is going to smooth out the high frequency residual error. Now let's do some tests and check what we need for this smoother. Let's check about the square domain, and B equals to a vector pointing from left to right top. Okay, now we test our problem with right-hand side f equals to 0 and the homogeneous Dirichlet boundary condition. So for this problem, actually, the exact solution is just a 0. We perform the solver with random initial guess and use our preconditioner several times, for example, 4 iterations, and plot U H minus 0, which is arrow. Okay, so here is arrow plot. As we can see, the arrow is actually stretched along this B direction. In order to smooth out this high frequency residual arrow, we may think about the stretching about this perpendicular direction. We can smooth out the high frequency arrow. So we apply one of the smoothing perpendicular line smoother direction, and here is the arrow plot. So the arrow will be reduced by almost 10. Okay, for this simple test, let's try about another B. So for this circular B, for example, like this one, we do the initial guess as the starting point and do the iteration for 4 times. And here is the arrow plot. As we can see, the arrow is very big. It's 1.4 E positive 3. Now we apply our smoother along the perpendicular direction. Then the arrow will be reduced to 0.5. And the reduction in the arrow is actually very significant, and that shows us the perpendicular direction of the line smoother works very well, and that's the idea for how to generate the smoother. Okay, so let's check how we generate the line smoother. So for example, we do some simple B. So for example, B is just a unit vector pointing up. We use our background mesh as the unstructured triangular mesh. Okay, so we can generate our line smoother by the following steps. First, we can delete the aligned edge. Then after dropping the aligned mesh, so for example, we can get here. Now we will sort out the edges which has almost the perpendicular direction to generate our line smoother. We first compute each edge's middle point. So for example, it's called the middle point of the edge. Then we evaluate B at this middle point. Then check about the tangential direction, inner product with this B, and do some scaling, okay, to compute the cosine of the theta. Theta will be the angle between the perpendicular direction and our edge. So this one quantity just tells us if we have a line mesh, this one will be very small. If we have the perpendicular edge, this one will be perpendicular. This one, sorry, I think I said wrong. For if it's perpendicular, this value cosine theta will be very small. If it's aligned, this one will be big. Okay, now we take 1 over this value plus some small value to avoid 0 bottom, and this will give the weight for each edge. So we compute the edges weights and loop all the edges and sort out the perpendicular edges. Okay, so for example, let's choose threshold equals to 2, and we'll sort out all the edges with weights bigger than 2. Okay, so here are the weights we computed for each edge. We will loop all of them. These edges, okay, so they are very big weights, so they belong to the perpendicular edge. So we'll add that to our graph. Then we sort the other edges with descending weight and loop all the edges. So the next one will be here, and we add to the graph. Then we continue about looping all the edges, and this one should be there too. Then this one, okay. Then if this edge has some vertex already in the graph, we'll connect these 2 edges. And we continue about this process. Now for this case, so we have 2 ending points with already included in the graph. So we'll connect these 3 edges to form one path. Then continue about the process. So still, we add that to our graph. Okay, now it's almost done. Okay, now here will be the line, the path cover for all the edges with weight bigger than 2. Okay, so we will add that to the line cover, and sort out all the DOF related with this line path. So for example, let's choose the path connecting point 19 to point 10. If we are using P2, we will sort out all the DOF related with this line cover or path cover. Okay. Okay, now let's do some tests. So for the smoother, for the DG method, we'll use the Gauss-Seidel smoother. And for the CG method, we'll use this construct block line smoother. And we'll use the multi-grade for the high order CG preconditioner. Then our preconditioner for our system, for our problem, is formed like the smoother for DG and some part for the CG method. And the preconditioner for CG is constructed by a smoother plus multi-grade for the high ordered CG method. We will choose tolerance for DG as 10 with power -6, and the tolerance for CG method with 10 up to -4. Okay, let's check about the similar test for this unit square with the unit vector pointing up. Here are the required iteration counts for the BDG in exact solver. We can observe this required counts is very similar as the previous exact solver. So this means our method works, and also we can observe the constant behavior if we are going up from K value and the D parallel value. So this one just tells us we have very robust results for our BDG in exact solver. Okay, now let's test our annulus test again. Yeah, by the way, the red figure plot the line path for our circular task. So here are the required iteration counts for different mesh size and different k value and the d parallel value. Also, we can see very good performance for big value in k for all the tests. Here I want to mention for the linear case, k equals to 1, we can observe the required iteration counts is actually not good for h equals to 1 over 12 and h equals to 1 over 24. Okay, so let's check about more details about the linear case. So for the linear case, let's check about the accuracy. Okay, so the blue line plot d parallel equals to 1. The green and this brown curve are d parallel equals to 1e positive 6 and 1e positive 8. Okay, as we can see, actually the numerical solution is not correct. For this case, there's no decaying for the arrow, and also for k equals to 1e positive 6. If h is fine enough to resolve the anisotropy, we can observe the decaying for the arrow. Okay, so this one means actually k equals to 1 with strong anisotropic doesn't work. And the condition number here may be not correct for achieving the accuracy we require. Then for the cubic mesh, we can observe very good performance for the arrow decaying. And for k equals to 5, we can also observe the decaying for the arrow. Oh, here I want to mention, you can see some limitation about this part. This one is because of our fixed tolerance. It's limited about our tolerance. If we change the tolerance with the smaller value, we may observe the decaying for the arrow. Okay, so the last test is about this shape. We construct a domain to mimic the West tokamak device and choose a sink and a source for the left and the right, okay, as this setting. We will choose our magnetic field as the circular shape for the test. Now, for example, let's choose d parallel equals to 1e positive 6. This is the plot for the numerical solution. And we also test the different values for the threshold. If we choose threshold equals to 2, okay, so that means the angle, we will sort all the edges with angle greater than pi over 3. If we choose eta equals to 1.2, that means we will sort all the edges with angle greater than maybe 30 degrees. If we choose smaller one, we will actually have more paths in our path cover. But from the figure, we can see little difference between different values in the line path or the line smoother. So actually, we can also observe numerical performance. They are similar. So for simplicity, let's only choose eta equals to 1.2. And here are the results for the required iteration count. If we use exact solver BDG on mesh with the size 1 over 10 and choose inexact solver on the same mesh, okay, for different values in the anisotropy and different polynomials degree, we can see the constant behavior, okay, for the iteration counts. So again, this validates our robustness with respect to the anisotropy and the k. Then comparing with the inexact solver and the exact solver, the required iteration counts, they are very similar. Okay, so this one also just tells us the inexact solver works, and we can use that to help us solve the problem. Okay, so as the conclusion, we are using high order scheme to resolve the numerical pollution on the non-aligned mesh. The auxiliary space preconditioner is employed to solve the corresponding linear system when we have the large anisotropy or very fine mesh or very high order in the scheme. As a future work, as you can see, actually the numerical analysis is lacking in all the talk. We will leave the numerical analysis and the rigorous theoretical proof for the future work. Our work has been done by ngSolve. I'm not very good in writing code. So in the future, we will incorporate with Mark and Dylan in the FEM implementation and achieve the exact saving or more savings by using FEM software. Also, we'll consider more applications with complicated magnetic field in the transport equation, and we will do everything as the future work. Okay, then here are two references about this talk. The first reference is about our anisotropic solver with aligned mesh. So it's already published at CPC. And the second reference is about the non-aligned mesh. We are using the same technique listed in this talk to solve the problem. And more details can be found in this reference. If you are interested, I can send you the copy of our reference. Then I go back to the outline, and I'm ready to take your questions. Thank you.
Thank you, Lin. Why don't we give her a round of applause? And then,
Thank you.
While we're doing that, does anyone have any questions for Lin? It's a very interesting. I like the line solver approach that you took there. That's pretty interesting. I haven't seen that approach to solving equations that end up with ill-conditioned kinds of matrices. So that's really interesting. Any questions?
This is Jerome Solberg. You can really have, conservation. You can demonstrate that in a, via post-processing for the CG method. And then you get rid of some of the issues you have with calculating alpha and stuff like that. Have you just compared the accuracy of just using CG on the same problem? Because you're building your preconditioner based upon CG, so you're kind of relying on that anyways.
That's right. Yes, that's right. So yes, so our scheme actually relies on the accuracy on the CG method. Yes, so I have not considered about the replace DG by the CG method. So probably we can think about that in the future work. That's a good suggestion from you. Thank you.
Yep, thank you. There's a nice paper by Hughes and stuff that talks about conservation in CG methods for the diffusion problem. So you should check that out.
Yes, yes, I will. Thank you.
All right, thanks.
I have a quick question. This is Tanya. Maybe I missed it, but what was the interpolation operator exactly that you used? Pi? Is it the averaging, or is it really an L2 projection?
L2 projection. So let me go back to that slide for the exact solver. So this one is just the L2 projection between CG and the DG space.
And these are really transpose of each other, pi and pi transpose?
Yes.
As matrices?
Yes, they are.
Okay. Okay, thanks.
Thank you.
I had another one. So have you considered, you think you can get anything by trying W or F cycles?
No, no, not yet. So this is just starting point. We have done this for 1 year, and the more complicated case and more advanced techniques will be employed in the future work.
Okay,
yeah, we'll definitely consider about that.
So that's something you've considered?
Yeah, not yet, but we'll consider that later.
Okay, yeah, I was kind of curious about that.
This is Mark. I have a comment and a question.
Sure.
Just in reference to Jerome's comment, very early on in this project, I did actually look at using CG, and I had better results with DG, and that's why we ended up going that direction. And I didn't study that as rigorously as I'm sure Lin would, so it would definitely be worth checking into that more fully. But there was some evidence or some indication that DG was a better choice.
I think, one of the things that we have run into, but that's more of solid mechanics with DG, is that, everything is so much dependent. And so when you move to a problem that starts to become more nonlinear, and I don't know whether that's going to be the case in your particular fusion application, but I guess, you know, depending upon the temperature and stuff, you might have some issues there. Then it just becomes harder, you know.
Mhm.
So that's just was my thought.
Yeah, it's a good point, and it's definitely worth, you know, a more rigorous investigation. So I'm really glad I've got Lin to help with this. The question though had to do with actually discovering those paths for the line smoother. How efficient is that? I know that Dylan has done some work in actually implementing this in FEM, and so we have a parallel implementation for an arbitrary mesh. And I'm wondering if you've looked at all at the efficiency of actually developing those line smoothers and how that scales as the mesh size increases.
Yeah, I didn't do any test about the efficiency for finding the path cover. Yeah, so I don't know. I need to ask you a lot of questions for scaling about this one and do the parallel implementation. I'm sure we can have some good way to do the efficient implementation.
Any hope of getting that implementation on a GPU? That looks like something that might be very messy on a GPU.
Yeah, I don't know. We'd have to ask Dylan about that. He's done this implementation and it works remarkably well. But I just wasn't sure if there was any scaling studies that I was unaware of.
Yeah. The is that code going in some kind of generalized form in FEM? That might be useful for other people.
Yeah, I'm not sure how generalized it is right now, but it would be
Yeah.
useful.
Yeah, just ways of building up these lines given a set of criteria that you'd want for them, right? I mean, that's for these hard solver situations. It's another tool in the toolbox, right?